Hello everyone, this is Adrija and welcome to the next video on Chinese Remainder Theorem. As the name suggests, it was time given by the Chinese. The Chinese mathematician Sun Zi gave this exact question in his book. Yeah, but he never gave a general question nor did he give a general algorithm to solve it. And the very first person to come up with an algorithm was Aryabhatta. So let's go. So the question goes like, if there are an unknown number of things, if we count by threes, there is a remainder two. If we count by fives, there is a remainder three, and if we count by sevens, there is a remainder two. This means that let the unknown number of things be x, and when we divide by three, we get a remainder two. So x is congruent to 2 mod 3. Similarly, x is congruent to 3 mod 5, x is congruent to 2 mod 7. So the Chinese remainder theorem says that any system which looks like this has a unique solution x modulo the product of these numbers. So that's stated in a general form. Suppose there are m1 till mr are positive relatively prime integers. So because they're relatively prime, it means that GCD of any two of them will be 1. GCD is the greatest common divisor, we call that. And suppose we go from A1 to AR being integers, consider the following system of congruences. X is congruent to A1 mod small m1, X is congruent to A2 mod small m2, and so on are many congruences of this form. Then the Chinese remainder theorem states that this system has a unique solution modulo capital M, where capital M is a product of all the small m's. Okay, let's look at a proof for this. So we define capital Mi, which is capital M divided by Mi. So it's basically the product of all the other small m's, leaving out the small mi. This implies that the GCD of small mi and capital Mi will be 1. And capital Mi, yi congruent 1 mod mi, we need to find the solutions yi in this. Okay, consider this congruence. Capital Mi, yi is congruent to 1 mod small mi. We know capital Mi, we know small mi. Small mi was given in the question. Capital Mi can be constructed from the information given in the question. And we need to find yi such that it follows this congruence. Remembering from our previous video, first you have to see the existence of solutions. So GCD of capital Mi and small mi have to be same as the GCD of 1 and small mi. So 1 and small mi GCD is 1, and here GCD of small mi and capital Mi is 1. So therefore solution exists, and because it's 1, you will have one solution modulo small mi. So we've got the solution of yi. Now we construct a z which looks like this. It's a1 capital M1 y1 plus a2 capital M2 y2 and so on. A1 is given in our question. Capital M1 can be constructed from the information given in our question, and y1 is what we obtained from here. We now attempt to show that z satisfies the system of congruence. Recall that our original system was x is congruent to ai mod mi. So if we divide x by mi, you'll get a remainder of ai. So we proceed to do that here. If we divide z by mi, we should get ai. That's our aim. So we'll see what we get. We're dividing z by mi. So let mi be this term. Okay. So note that capital M, all the other terms, all the j terms will have small mi in its product, because capital Mi is the product of all the small m's other than mi, small mi. So all the other, say, capital Mj terms will have the number small mi inside it. So when we divide it by small mi, we get a remainder of 0. And the only term remaining, which is not divisible, it does not have a factor, is ai capital Mi yi mod mi. And note that from here, capital Mi yi is congruent to 1 mod mi. So ai capital Mi yi will be congruent to ai mod mi. So therefore, we see that Z satisfies the system of congruences, and this was a proof for existence of solution. Next, we need a proof of uniqueness. That is, there is only one unique solution modulo capital M. And I'm going to leave that to you. Try to think about it and solve it. It's very simple. That's what we do. For any kind of uniqueness proof, we assume that there are two numbers which satisfy it, and then we try to show that those two numbers are nothing but the same. We're going to do the same thing here as well. Let both x and y satisfy the system of congruence. And after that, I'll ask you to proceed with it. And finally, you have to show that, this is a hint, finally show that x minus y mod capital M will give you 0. This implies that x is congruent to y mod M. That is, x and y are equivalent modulo capital. There's only one value in the range of 0 to capital M minus 1 which satisfies this system. So that's the proof of uniqueness. And that's it for this video. Thank you. Bye.